Okay, let's work some more sample problems for reaction kinetics. This is from chapter 13, problem 33. Here at the beginning of the chapter, we want to learn how to compute both average and instantaneous rates of chemical reactions. And this problem really helps us do that. It shows some examples. We're supposed to consider the reaction H2 plus Br2 to make 2 copies of HBr. It's all gas phase to gas phase reaction. We're supposed to consider that reaction, and this graph that's given in the textbook, it's probably a little bit difficult to make out some of the digits in this graph, but basically it's a plot of the concentration of Br2 as a function of time over about 2 minutes. Okay, if you look at the problem up in your textbook, it's 1333 at the end of the chapter problems. You could follow along, using that plot, and I encourage you to do that because this is basically going to be the source of our data for our analysis, right? So we're asked a couple different things. First, we're asked what is the average reaction rate over 0 to 25 seconds. We want to know then the instantaneous rate at 25 seconds, and what is the instantaneous rate of formation of HBr at 25 seconds. I think I've actually changed that. I think it was 50 seconds in the book, but I changed it to 25 so I didn't have to do the graphical procedure over again that I'm going to show you all. And I'm going to capture the stoichiometry change and the reaction without having to sort of redo a lot of work. Okay, so let's go through this and see if we can answer these questions. All right, so the first thing is A, computing the average reaction rate. Okay, this is the average reaction rate over some period. Now, you're always going to be told the period or the time range. Here it's 0 to 25 seconds, okay? You're always going to be told that because to compute the average, you need to know which time range they're speaking of, okay? So if I'm going to compute the rate of reaction, I can always do it as change in concentration over change in time. Okay, so that's kind of where I'm going to start. Now, again, I like to gain momentum. Doing things that are relatively straightforward. So I know my delta t here is going to be 25 seconds, 25-second range that was given to us. But I need to figure out my change in concentration. So change in concentration of what? Well, I'm given this data here that's a plot of the concentration of one of the reactants, the bromine, as a function of time. Okay, so I could basically look at this plot that's given in the book and extract out of it the data that I need to use for my change in concentration. Remember, my change in a value is always my final minus my initial. Okay, so C final minus C initial. Now, if I look at the final 25-second point on my plot, it would be right about in through here. This is 30, this is 25, so on the data plot, right about there is my 25-second point, okay? Initially, my concentration is right at 1 mole per liter. But by the time the 25 seconds elapse, it looks like my concentration is significantly lower. You're down about 0.76, I'll say, if I read it off here, okay? 0.76 moles per liter. So I take my final concentration, 0.76 molar, and I subtract the initial molarity, which is 1 molar. Now, since I'm tracking the concentration of a reactant, something that's consumed by convention, I always multiply again by -1. That's just something that's done to express the reaction rate as a positive and not negative number, okay? Because we are, in fact, using this out over time. So continuing out the math, I have 0.24 mole per liter consumed in 25 seconds. If I do the math on that, it looks like my rate is 0.0096 molar per second. That's my average rate over the first 25 seconds of this experiment. Okay, so I'm asked for the average rate. Look at the change in concentration, just divide by the change in time over the gap in time you're given. It's easy enough, okay? Now, the next follow-up question, part B, asks me something different. In part B, I want to know the instantaneous rate at a particular point, a very specific point in time. In other words, if I could take a snapshot of the rate at 25 seconds in this case, right, what would that rate be? Measurement of instantaneous rate is important because that's what we use to develop our rate laws. So we have to be able to measure instantaneous rates based on laboratory measurements. That's important to know. It's not the same as the average rate. The instantaneous rate is the rate at one very specific point in time. That could be the beginning of the experiment. It could be after some time, but very, very, very specific point in time. We want to know at what rate is the reaction proceeding. So in this case, it's 25 seconds. So how are we going to figure that out? How in the world can we do this? Well, let's take a look at our plot. Concentration of bromine in time. All right? Right here is that 25-second point. I want to know the exact rate of the reaction right at that point. That's what the instantaneous rate is about, okay? Now, how can I figure that out? Well, this is a plot of the concentration in time. So at every point along this curve, there is a slope that's associated with the function that describes the shape, right? That slope is the reaction rate at that point in time, all right? The slope of this curve basically tells us the reaction rate at any point in time. So all we really need to do is pick out the special point that we've been specified here as 25 seconds. That could be any time, right? It could be the beginning, the end, it doesn't matter. The problem just says 25 seconds. And we write in, on our plot, a tangent line at that point. The tangent line is a straight line that touches our graph or our data plot right at the point of interest and basically nowhere else. It's meant to measure the slope of a line at that very point. And we can add it in such that it's basically a good estimate of the slope right at that 25-second point. And then what we can do is just a little bit of graphical analysis, more or less kind of like geometry here, rise over run type business, to figure out what the slope of this line is, right? Because the slope of that line is consistent with the rate right at that 25-second point. And that's what I want to know for part D, that instantaneous rate right there, okay? Right at that point. So I've gone ahead and got myself a straight edge here, okay? And I would actually draw in on the graph a tangent line that basically intersects right at that point, right? And then I just measure the slope of that line, which is representative of the rate. Now, to help me do that, I have to remember that the slope of my line, m, is equal to the change in y variable divided by the change in x. I'm going to invoke that bit of mathematics here. So to figure out how much my y variable changes, what I'm going to do is I'm going to consider this tangent line extrapolated all the way back to my y-axis and all the way forward to this point, which is right at 60 seconds, okay? So I'm going to extrapolate my line forward and backwards such that it comprises this whole first minute. I'm just doing that for ease of measurement. It's a little bit arbitrary. I mean, I could pick 20 seconds or 40 seconds and different intervals here as well, okay? But I'm doing that just to have something to work with for my slope computation, right? So moving forward then, what is my change in y? Well, that's going to be from 0 to over 60. It looks like right here. Oh, that's a tough one, right? But where does that line intersect at 0? It looks to me like maybe it's 0.96 molar units. It's pretty close to the 1, but not quite there, okay? So that's going to be one of my molarities. In fact, that's the initial molarity. And then right here at 60 seconds, if I look at where that's going to intersect, it looks like a little bit less than 0.5, so I guess I'll call that 0.48. You might wonder why I'm writing this in this order. But I want it to be consistent with this final minus initial business. So C final, C initial at time equals 0. It's the higher number. So again, since I'm consuming reagent, I'm going to give it a negative sign here just to be consistent. and have it be a positive rate of progress. But nonetheless, that is my concentration change over the first 60 seconds of this experiment as determined by, not by the actual data set, but as determined by this tangent line. So when I report these numbers, I'm not looking at the points along the curve, the data set's given. I'm looking at my actual tangent line to get those numbers, okay? And that's important to realize. Now, same thing for my delta x, but this one's easier because I did it, and I've already explicitly said that I've done this exercise from 0 to 60 seconds, okay? So clearly, my elapsed time, or my delta t, was 60 seconds, right? So that one's actually kind of a freebie. It's pretty easy to come by. But if I do the math on this, I find that the rate of reaction is 0.008 moles per liter per second, or 0.08 molar per second. It's my change in concentration per unit time. Here we specify time in seconds and concentration in molarity. All right, so that is my instantaneous rate at t equals 25 seconds. Okay. Now, is that the same as the average rate over the first 25 seconds? It is not. We determined the average rate was higher than that in part A. It was 0.0096, if you recall. It's lower than the average rate. They're different. They're not the same because they're describing different things. The average rate is the mean or the average over this entire period, but in reality, the rate changes during that 25-second period. All right? The instantaneous rate tells us what the rate is right at that 25-second point. If I computed it for t equals 0, I get a different number. It would be larger than what I computed, okay? But we got to understand the difference between these two. Now, the last part of this problem asks me something different. It says, what is the instantaneous rate of formation of HBr at t equals 25 seconds? Okay, what's the instantaneous rate of formation of HBr at 25 seconds, which is the same as I just did this calculation for, right? Okay, so what I found here, essentially from the data, was the rate of consumption of my BR2, all right? Now that corresponds to the overall rate of reaction by virtue of the 1 and the 1 in here for the stoichiometry, okay? But the thing is that my HBr is produced at a rate twice the consumption of my Br because of the stoichiometry, okay? So if my overall reaction rate is this, and the rate of consumption of the H2 or the rate of consumption of the Br2 is this, which it is, it stands to reason then that for C, the rate at which the HBr is produced is 2 times the instantaneous rate of use. So my instantaneous rate of production would be 0.016 for my 2 HBr, okay? So moral of the story is you gotta be real careful about what the question's asking you, okay? In this particular case, I mean, it just kind of reads right off the tongue and you might not even realize what it's saying, right? But you want the instantaneous rate of formation. So it's not an average rate, it's the instantaneous rate, okay? So that's one thing to consider. And you want the rate of formation of a particular compound, okay? So you want to quantitate the rate at which this particular compound is formed, not the overall reaction rate where you divide out by the stoichiometric coefficients. Here you want this particular compound, and that's why we had to multiply by 2, okay? So you got to be real careful about the wording, I think, for these problems. If it's asking for a specific compound, you're going to have to probably multiply the reaction rate by the stoichiometric coefficient to make that happen, right? But if it's just asking for the reaction rate, that is the one that basically we use the data and we divide out by the stoichiometric coefficient to express the overall reaction rate as if the stoichiometric coefficient was equal to 1. Okay? And we just do that by convention just to make things easy. All right, well, nonetheless, this was problem 33 from chapter 13.